With all of the previous information in hand, we are ready to write our equations for the deflections. As a starting point for doing this, we define delta 1, 0 as being equal to 0, where this is the displacement in the original structure at redundant position 1. And we know that in our original structure we did not specify any sort of deflection. It was a support and no displacement at that location. So I'm defining it as delta 1, 0. We also have delta 2, 0, and it is set equal to 0, which says that the original structure has 0 deflection at redundant 2. So that's the same as at position 1. We have no displacement, but we're just creating some variables to indicate the displacements at those locations. Now, in order to write our equations for the deflections, I want to kind of review what we have done here. We have the original structure. We constructed a primary structure, and we've indicated the displacements at each of the redundant locations due to the applied loading. We've also drawn structures for the loading where we have only the loading of redundant R1, and we've also drawn a structure where we have only the loading of redundant R2, and we have indicated the corresponding displacements that occur in each of those situations. Now I want you to notice that we have always been careful to apply these redundants in the positive sense, and we have also indicated our displacements in the positive directions also. This is very important when doing the force method. By being consistent and doing that way, we will find in the end that if our assumed directions were incorrect, we will just get negative values, and it just indicates that our redundant reactions are really heading in the negative direction. Once we have those three structures created, they are three statically determinate structures, whereas our original structure was statically indeterminate. So then, the superposition of those three structures should be equal to the original structure. So, considering now position 1, we are going to write our deflection equation. And we have that the deflection in the original structure is equal to delta P1 plus delta 11 plus delta 12. And this is all for position 1, which is the vertical direction at node C of the original structure. We can also write a deflection equation for position 2. In this case, we have delta 2, 0, which is the deflection in the original structure at position 2, and we also then have on the primary structure that is equal to delta P2 plus delta 21 plus delta 22. And so now we have our equations for the deflections. Next, we can write our deflection equations in a different way. And so I have done that here. We have that delta 10, the deflection on the original structure at position 1, is equal to F11R1 plus F12R2 plus delta P1. And the displacement on the original structure at redundant 2 is equal to F21 times R1 plus F22 times R2 plus delta P2. Using these two equations up above, we need to insert into these variables information that we have found previously. For instance, previously we found Fij values, we also found delta P values, and we also found delta I0 values such as delta 10 or delta 20. So if we do that very thing, we insert that previously found information, these equations up here simplify to the following. We have 4/3 L cubed over EI times R1, where this front material here, this coefficient in front of R1 is F11. We also have plus 3/2 L squared over EI, and that is F12 times R2. And then we have taken delta P1 to the other side, and we get it equal to negative ML squared over EI. And we're not seeing delta 10, of course, because delta 10 is actually 0. No displacement at position 1 in the original structure. We can do the same sort of thing, plugging in our known values, and we get this second expression here. 3/2 L squared over EI times R1 plus 2L over EI times R2 is equal to negative ML over EI. The next thing that we want to do is we want to take this last two set of equations and we want to write them in matrix form. And we also note that all of the EI's are going to cancel, and so those will be eliminated. And writing that expression, or those two equations, in matrix form, we find this matrix expression here. We have 4/3 L cubed, 3/2 L squared, 3/2 L squared, 2L, and that 2 by 2 matrix is multiplied times our unknowns, R1 and R2, and that is set equal to our expressions that this matrix equation is equal to, negative ML squared and negative ML. Before we proceed to solve our matrix equation for the unknowns R1 and R2, I want to review a procedure from linear algebra called Kramer's rule. And it will help us solve for the unknowns R1 and R2. Now, supposing that we have a 2 by 2 matrix, and we also have our unknown values in a vector form here, R1 and R2, and we have these values B1 and B2 in this final vector. We have a generic expression for a matrix equation, and so we have a matrix A times a vector R is equal to a vector B. And we want to solve for our unknowns which are contained in the vector R. And we can do this using Kramer's rule. In order to do that, we're going to have to use the idea of determinants. The first determinant that we want to find is what I'm going to call the determinant dr1, and it is equal to this matrix A, but with the first column replaced with the B vector. And so you can see this matrix now is B1, A12, and B2, A22, and we would want to be able to find the determinant of that. We also are going to need to find a determinant that I'm going to define as dr2, where we have replaced the second column of matrix A with vector B. And so we see A11 times B1 and A21 and B2. And so we will find the determinant of that matrix. And lastly, we're going to need to find the determinant of the matrix A itself. And as an example, to remind you of how a determinant works for a 2 by 2 matrix, it will be A11 times A22 minus A12 times A21, like this. And so then that's a general expression for the determinant of a 2 by 2 matrix. With those determinants in hand, we can use Kramer's rule and solve for those unknowns R1 and R2. R1 is equal to the determinant R1 divided by the determinant D right here. And the unknown R2 is equal to the determinant dR2 divided by the determinant D. And that is application of using Kramer's rule. We now want to apply Kramer's rule to our particular problem. And we want to solve for R1 and R2, and this is the matrix expression that we found previously. And so we need to find those various determinants that are necessary to use Kramer's rule. The first thing that we're going to do is we're going to put this B matrix as the first column in the A matrix. And so we've done that here. And we can find then the determinant, which we call dR1. And it is equal to, after we take the determinant here and simplify, we get this final expression. It's -1/2 ml cubed. We also are going to do the same thing for dR2, but here I've also, for dR1, I have written out exactly how that determinant expression is taking place. We have this term times that term minus that term times that term, and it gives us this final answer here. We also need to find our determinant for dR2, where we have put in vector B in this last column of the A matrix. And if we take the determinant of that, we get finally ml to the 4th divided by 6. And lastly, if we take the determinant of the A matrix, multiplying this times that minus that times that, we get 5/12 L to the 4th. With the determinants in hand, we can now calculate our unknown R1, and it is equal to the determinant dR1 over the determinant D. And so doing the algebra, plugging in the values for each of those terms, we get -6/5 times m over L. And for R2, we get the determinant of dR2 over the determinant of D, and that is equal to this expression here. Doing the algebra on that, we finally come to 2/5 times m. Now we need to draw a free body diagram of our original structure with our known reactions applied. So I've drawn that structure here. I have the applied moment m. I have the reaction R1 pointing downwards here, 6/5 of m over L, and the moment at position 2 of 2/5 m. I also have indicated these unknown reactions down here at joint A. I have a shear, I have a axial force, and I also have a moment at position A. If we sum forces in the x direction on this structure, there's only one horizontal force, and that is VA. So the shear reaction at position A is equal to 0. We can also sum forces vertically, and so we have NA minus 6/5 m over L equal to 0. Solving for NA, we get that NA is equal to 6/5 times m over L. Lastly, we can solve, or rather write an equation, a moment equation, about point A and set it equal to 0. And we're choosing counterclockwise as positive. And so if we start by summing moments about point A, we see that we have an applied moment of m. We have this reaction at position 2 of 2/5 m, and both of those were counterclockwise moments. We also have MA right here, and that's indicated, assumed in the positive direction. And lastly, we have this reaction over here that is causing a moment about point A, and that is 6/5 of times m over L times this moment arm of L. And so we have 6/5 m over L times L, and that's a negative moment causing a clockwise rotation about A, and all of that is set equal to 0. Well, if we do a simplification, do some algebra here, and solve for MA, we get that MA is equal to negative m over 5. That concludes finding all of the reactions for our original structure, and we did that by using the force method. So hopefully that's helpful to you as you consider the force method on frame problems.